My name is John Holmes from JDH Consulting Australia, and this video today is going to discuss analysis and prediction of extreme wind speeds and loads. It was previously given as a PowerPoint presentation at a conference, and we just converted it into a video to make it more widely available. I'd like to acknowledge my co-author, Dr. Chi-Sang Wang from CSIRO in Australia. Extreme value prediction of any variable is a huge topic. There's a vast number of methods and techniques available that you can find. But this talk, I've just selected 6 topics that I found useful in predicting extreme wind speeds and responses. So you can see those listed there. The first one, return period versus average recurrence interval. I'll explain the difference between those two quantities. The second one is concerned with pre-processing of wind data before you start thinking about fitting distributions. And then we come on to the 2 extreme value distributions that I found most useful: generalized extreme, GV, and generalized Pareto distribution, GPD. Then the next topic is fitting of those distributions with a fixed shape factor. And I'll discuss 4 methods of doing that. Once you've got your distribution sorted out and plotted and are trying to make predictions of extremes over long average recurrence intervals, you need to think about the errors involved. And one way of doing that is using bootstrapping to get confidence limits. Then the final topic is to do with predicting of wind loads and response, for which you need to allow for wind direction variations. Now, there are 2 measures of time that are used in extreme value probability. One of them is return period. This was defined in 1941 by Gumbel and is outlined also in his book from 1958. You can see the cover of the book on the slide. Now, return period is defined as the reciprocal of the probability of exceedance of an epoch maximum. Usually the epoch is taken as 1 year. Now, since probability cannot be greater than 1, the return period cannot be less than 1. Now, the other quantity is average recurrence interval or mean recurrence interval. Now, this is defined as the reciprocal of a crossing rate of high values by a stationary random process. An average recurrence interval can take any positive value, so it can be less than 1 year. But often return period and average recurrence interval are treated as the same quantity, but they're obviously not. Now, in order to get a mathematical relationship between average recurrence interval and return period, we're going to consider the probability of a particular value of wind speed, could be any variable, we'll use wind speed, being the maximum value in a time t, and we'll set that time t to be 1 year eventually. So starting off with the average recurrence interval way of doing it, we're going to consider the number of exceedances, which is obviously an integer number, of a wind speed v in a given time period t, and the appropriate distribution for that is the Poisson distribution. You can see the expression there. Mu is the mean number of exceedances in the time t, and that can be directly related to the average recurrence interval, which we're calling r subscript I. You can see that relationship there. Now, to get the maximum value of v in the time t, well, we need the probability of a 0 exceedances in that time. So we set n equal to 0, and that gives us that expression there, x minus t on Ri, as the probability of v being the maximum value in time t. And then we can, of course, set t equal to 1. So that's one way of doing it. Now, the other way of doing it is to use the return period. And by definition of return period, the probability of non-exceedance of v in 1 year is 1 minus 1 over Rp, where Rp is the return period. So now we have these 2 expressions for the probability of v being the maximum or its non-exceedance in 1 year, which is the same thing. So right at the bottom on the slide there, you can see that relationship between RP, the return period, and RI, the average recurrence interval. This slide shows a plot of average recurrence interval against return period. Average recurrence interval is the abscissa or x-axis, and return period is on the y-axis. So that's based on that relationship we derived on the previous slide. So two things about that graph. One of them is that the return period never goes below 1, and we mentioned that earlier. So that graph clearly shows that at the left-hand end. At the right-hand end, you'll notice the graph converges, or the return period converges with average recurrence interval. So they become almost the same after about 10 years. Interestingly, they don't actually converge completely, and there's a mathematical reason for it, which we won't go into here, but there's always half a year difference. Return period is always, even in the limit, at the high end, there's always half a year. Return period is half a year greater than average recurrence interval. This slide and the next 5 are devoted to the pre-processing you need to do to before you start making predictions from recorded extreme wind data, namely the separation and correction of recorded wind data for various aspects. The first thing we'll talk about is the separation of different types of wind, extreme wind events. And the main two we're going to discuss here are the synoptic wind events, large-scale wind events, large-scale pressure systems from non-synoptic or transient winds, usually produced by thunderstorms. So what we show on this slide here is an EMA graph, a wind speed versus time. And the time on this graph here is actually the whole time is 1 day. So we're looking at a day of wind and wind speed and a day of wind direction. So for synoptic, large-scale synoptic events, the wind speed is relatively stable. You wouldn't call it constant, but it's relatively stable. It doesn't change very much. You've got fairly strong winds over the whole day, and also the wind direction stays very constant over that day. So these are what we call well-behaved winds. Wind tunnel modelers like them because these are the ones they can easily simulate in a wind tunnel. But not all winds are like this, unfortunately. Well, this is another EMA graph. In this case, it's half a day of wind speed. And this one is from a thunderstorm downburst, which is a non-synoptic type of wind event. You can see it's quite different to the previous slide. It's quite different to the synoptic wind trace. You have a sudden increase in the gust wind over a very short period, and then it decreases again as the storm front passes by the site. And this one shows a gust factor ratio between 3-second gust and 10-minute mean of well over 3. So this is not your standard boundary layer wind, unfortunately, and in many parts of the world these winds are the dominant extreme wind event, usually less than 30 degrees latitude north and south of the equator. So we need to consider these as well, and in many places we have a mixture of synoptic and non-synoptic extreme wind events, and they need to be separated and separately analysed. Well, another thing you may need to consider if you're dealing with gust data is to correct for the gust duration. And you may want to do this if you're in Australia, because the standard in Australia uses a 0.2 second gust, whereas the recordings by the Bureau of Meteorology are of 3-second moving average gusts. And this plot here shows another time history of wind speed, the 3-second gust and the 0.2 second gust for a tropical cyclone or a typhoon. And you can see there was quite a bit of difference, especially at the peak of about 15%. The 0.2 second gust is 15% higher than the 3-second gust. In order to make the correction, you need to know turbulence intensities and peak factors. I don't have time to go into the details of it, but you can find that plenty of papers on that. Now, another correction you will probably need to make for recorded wind data is to correct for terrain. Now, a lot of anemometers operated by weather bureaus are located at airports. Usually the terrain is pretty flat, but the roughness can vary. And you can see the example there of an airport location. To the southeast there's the airport buildings, and to the northwest there's a patch of forest. So those will probably need to be corrected for. Now we've superimposed on the Google Earth image what you could call a wagon wheel or a pizza, which shows the various direction sectors. And from that you could assess the terrain and make corrections on that basis. Another way of doing it is to use recorded gust factors from which you can get turbulence intensity, and following that roughness length, and then make your correction factor a bit more scientifically. But that does require a lot of recorded data, and that is applicable really only to synoptic scale winds. Well, having separated our recorded wind data into different wind types and corrected for terrain and, if necessary, gust duration, we need to choose a extreme value distribution to fit to the data and then make predictions from it. The one I've found the most useful is the generalized extreme value distribution, or GEV, with a small positive shape factor. We'll talk about the shape factor in a later slide, but what we're showing here, that first equation, is the general equation for the complementary cumulative distribution of the GEV, written in terms of return period. The return period, obviously, reciprocal return period is the probability of exceedance of a particular value VR. Now, at the bottom of the slide, we've rewritten the equation in terms of not return period, but average recurrence interval, RI. And it actually turns out it's a much simpler form. The box at the bottom left is actually the form there written in terms of RI, and we have two parameters, in fact, A and B, and these involve the three basic parameters of location, scale, and shape factors. Now, the other distribution I want to discuss in this talk is the generalized Pareto distribution, or GPD. Now, this is a distribution for excesses or peaks above a threshold. For example, for wind speed, you may have a threshold of 20 or 25 meters per second. The GPD is a distribution for the difference from that threshold, U0. Now, knowing the rate of crossing of the threshold at U0, which we call lambda, you can then calculate the average crossing rate of a higher wind speed, say VR, by that formula there, and the red ringed distribution is the GPD. Knowing that crossing rate, the reciprocal of that is the average recurrence interval, RI. So following that through, down at the bottom left, we have the same basic equation for the distribution that we had for the GEV. The difference with the GPD version of it is that the A and the B are slightly different, defined slightly differently. But clearly the GEV and GPD are very closely related. Now, there were a number of factors shown on the previous two slides in relation to the GEV and GPD. Probably the most important one of these is the shape factor, K. Now, there are three possibilities. K can be positive, negative, or 0. And each one of those possibilities relates to three different types of extreme value distribution. When K is equal to 0, the GEV and the GPD revert to the type 1 or Gumbel extreme value distribution, which is commonly used by lots of people, particularly in wind engineering. But there's a bit of a misconception that you can't use the GPD and the peaks over threshold method for the Gumbel distribution. That is not the case. But the mathematics is a little different. As you can see from the equation in the middle of the slide there, it involves the natural log of Ri rather than Ri to the power of negative k. Now, we prefer to use a positive shape factor. For example, in the Australian standards on wind loading, k is plus 0.1. One reason for this is, or probably the main reason, is that it will give you an upper limit. And we believe that any type of windstorm, the atmosphere will not give you unlimited wind speeds. Now, over the next few slides, we're going to consider several different methods of fitting the GPD/GV to a set of data. And of course, we've got a fixed shape factor K. So at the top of the slide there, you can see the basic distribution. We fixed K, so we just need to determine A and B. Now, the first method, which I've called method 1, is very simple. It uses GPT, and hence it's using peaks over threshold or excesses over threshold data. And I've laid out the steps there. So this simple method just uses one threshold, which we call U0, which could be 25 meters per second, for example. And to use that method, we tabulate the data and tabulate the excesses of each value above that threshold and average them, and we call that E. Also, we calculate the average rate of exceedance of U0, of which we call lambda. And knowing those, we can substitute in the equation down the bottom for E. And actually, E turns out to be, or E times 1 plus K turns out to be the scale factor sigma, which is part of the GPD form of the distribution. It turns out this method is actually effectively the method of moments, which you may have heard of before. It's a very commonly used method for fitting any distribution. But because we fix K, we're only using the mean. The standard deviation excess is not required for this simple method. Well, on this slide, we've shown the complete set of calculations for the method 1 as applied to a set of gust data, 26 years of gust data, which produced 23 values greater than 25 meters per second. So over on the left, we've tabulated the values in their order of recording. And on the right-hand column, you can see we've tabulated the excess of the gust above the threshold of 25 meters per second. So, for example, the first value of 29.2 gives you an excess of 4.2 meters per second. And continue that all the way down, and average. That gives us the E value of 4.5 meters per second. Now, the rate of exceedance of U0 for the data is 23 and 26 years, 0.885 per annum. So knowing those two values, we can calculate the A and the B, as shown on the right-hand side, and that gives us a distribution. 74.5 minus 50.1 times Ri, the average recurrence interval, to the power of negative 0.1. Now, plotting that value against the data is down on the bottom. We see it's not a bad fit to the data, and it gives us a prediction of 500-year average recurrence interval value of 47.6 meters per second. Now, the second method we're going to look at for fitting GPD with a fixed shape factor is known as mean exceedance, or conditional mean exceedance, which I've called method 2. It's due to Davison and Smith from 1990. Again, it's quite simple, a bit more complex than the method 1, and it's related to the fact that the property of the GPD and excesses over threshold, that if you plot the average excess over several thresholds, you plot the increment of the thresholds on the x-axis and you plot the average excess on the y-axis, you get the sort of plot that's shown on the top right there. And they should come out as a straight line, or approximately a straight line. Now in this case, if we're fixing k, the slope is fixed. And if k is equal to 0.1, for example, the slope is minus 1 on 11. Now all we need to know to make predictions is the intercept of that straight line. And as you can see halfway down the slide there, that can be calculated from the average of the increments of the thresholds above the lowest threshold, U0, and E bar, which is the average of the mean excesses over all n thresholds. And knowing that, through the red arrow there, we get our sigma hat and substitute in our basic equation to give us the predictions. And now we come to our third method of fitting the generalized extreme value distribution to the data. This one doesn't involve the GBT. This is just direct fitting of GV to the data. And the way we can do that is to rewrite our basic equation, the VR equals A minus B times Ri to the power of minus K, rewrite that as Y equals A plus BZ, where obviously Y is equal to VR, and Z is a new variable, which is minus Ri to the minus K. So the way of doing that is to take the data and estimate empirical values of Ri from the data, knowing the number of years and the number of occurrences of the values, and just doing a standard least squares fit as shown on the graph there. And of course, with that form, that Y equals A plus BZ, the intercept is A and the slope is B. So that gives us everything we need to make predictions. And you'll see on the graph that this particular example, the intercept, or A, is equal to about 70 meters per second. The fourth and final method we're going to look at for fitting some extreme wind data to GPD/GEV is called maximum likelihood, method 4. Now this is a method that's very popular with statisticians. They regard it as the best method of fitting, actually. So it involves this likelihood function, L. Likelihood is just another name for probability. So the idea of this, the method is to maximize the ability of a particular function, in this case it's the GPD, to fitting the data every point on the data. So it's maximizing that likelihood of fit. Now this, in our particular case, we're fixing the shape factor K, so the only parameter we're trying to optimize is the scale factor sigma. So you can see on the plot at the bottom that log likelihood function for the GPT for that particular set of data plotted against sigma. And the value that gives a maximum value of log L is 4.733. So that's our optimized value that we need to use. The rest of it follows as previously. Once you've got your sigma, we know the K, we can make the predictions as we did previously. As I said, it's regarded as the best fit by statisticians. It's a bit cumbersome to use because you need an iterative numerical solution for it. Well, on this slide, what I've done is summarize in plots the 4 methods that we've discussed and shown how the lines predicted, the GEV/GBD lines of gust speed against average recurrence interval, how those lines fit to the data. The data was the same data I showed a few slides back, the 26 years of gust data. So top left is the first method, the so-called simple method, which is really method of moments. Second method, top right, is this conditional mean exceedance. Bottom left is direct least squares fit of the GEV. And finally, method 4 on the bottom right is the maximum likelihood method. And I've also shown on the graphs there the predicted values of the gust wind speed for 500-year average recurrence interval. And you can see they vary between 44.8 from method 2 to 47.6 for method 1. That's a variation of about 6%. The other two methods, 3 and 4, gives values in between. So hopefully that's given you some idea of the options available. There are probably several other methods that we could use, but 4 is probably enough to go on with. Now moving on to the next topic, bootstrapping and confidence limits. So if we've developed a function of, say, gust wind speed against average recurrence interval, using one of those methods that we discussed earlier, we want to know how reliable or how confident are we in making predictions at longer values of average recurrence interval based on that distribution. Now for some distributions, probability distributions, there are theoretical confidence limits that you'll find in papers and textbooks, but not for every distribution. So there's another way of doing it. It's known as bootstrapping, which is a strange name. It's nothing to do with bootlegging or boot scooting. Bootstrapping, I'm not sure how it got its name, but basically it's a simulation technique that involves using random numbers and using the same number of data points that you started off originally with to make your original function, but changing the values to random numbers within a range, and you end up with multiple different fits or multiple different distributions that could have come out of that set of data. So what you see there on that graph is one case where that's been done. So the solid line in the middle is the actual fit to the data. The dashed lines are these simulated fits that come from the random number generation. And that only shows 15 fits, which is not going to be enough. Normally you'd go for 50, 100, even thousands. Just use a computer to keep churning them out. And once you've got enough of those there, you can develop confidence limits. In other words, the range plus or minus percentages, if you like, of outside of the fitted line that the simulations produce. So this slide shows 80% confidence limits on the 500-year average recurrence interval wind speed for the same data that was on the previous slide. This is based on 144 station years of gust data in this particular case. So this time we're just showing the plus or minus 40% confidence limits on that nominal value in the middle, which comes from the fitted distribution. So for that particular example there, the prediction is around 44 meters a second. The confidence limits though give us a range of 41.7 to 47.1 meters per second, which is around 5 or 6%, I think. That's based on 144 years of data, so we wouldn't expect anything any closer than that. Well, now we're going to change topics a little bit. Methods of treating directionality. So why do we need to introduce wind direction as well as wind speed? Well, we're not just interested in predicting wind speeds, we're interested in predicting structural loads or structural response and shape factors which kind of relate the structural load or the response or wind pressure relating to wind speed will vary significantly from direction to direction. This is something you can get out of a wind tunnel test. So that needs to be incorporated. So this is where the wind direction comes in. Now, this is, again, it's a pretty complex subject. I'm just going to touch on part of it and look at two different methods of doing it. We'll start off with the more simple one, which is called multi-sector method, which actually I came up with a long time ago. Was it 30 odd years ago? I didn't give it a name at that stage, but since then it's developed its own name as multi-sector method. It's really as simple in concept. All we're doing is endeavoring to fit or come up with distributions of probability distribution for each direction that we're interested in, each of the n directions, for the probability of a response, excuse me, say m, which could be a base moment. And then assuming that the directions are independent from each other, then we can just multiply the cumulative distributions from each direction, multiply them together to get the combined probability of response m from any direction. Now basically the only assumption is this independence of wind speed from adjacent direction sectors. But there is a bit of a disadvantage. You need to have pretty good long and fairly long wind data records to be able to develop those distributions. And ideally you'd need 8 or 16 different directions to work with it. Well, the top equation here is the same equation from the previous slide, just rewritten in terms of return period, RP. And for a given wind speed, you have, of course, a different return period for each wind direction. So that's just the same expression. Now, it's interesting to actually rewrite this expression in terms of average recurrence intervals, which, as I showed earlier, is different from the return period. Now, when you do that using that relationship at the bottom between return period and average recurrence interval, you get even a simpler expression. So 1 over the combined recurrence interval is the sum of the reciprocals of each of the recurrence intervals from each of the direction. So it's interesting that using average recurrence interval generally makes life a little simpler for some of these calculations. So now we come to another method of dealing with directionality and predicting extreme structural responses, known as the outcrossing method, which originated again with Professor Alan Davenport from the 1970s. What you saw on the right there was there's sort of a graphical summary of it. Now, unlike the multi-sector method, which is based on distributions of extreme values of wind speed, like annual maximum, that kind of thing, this method is based on the parent distribution of wind speeds. In other words, all wind speeds, the whole population. And because we're separating out each direction, you need a distribution for each direction. Usually a Weibull distribution is what's used. Now what this method does is essentially try to predict the rate of crossing of the wind speed from any direction of that boundary, the dashed line and the boundary there on the right, which is something you can get from a wind tunnel, which is sort of shows the variation of structural response or shape factors with wind direction. And the formula on the top left is the formula for the rate of crossing of that boundary, the two-dimensional boundary. And it's a development of the Rice's level crossing formula that some of you may have heard of before. So it's a little complex, and that's one of the criticisms of it. Actually, it's fairly complex to understand and even to use. I suppose the main advantage of it is that you supposedly, if it's all the assumptions are satisfied, that you can get results with just having the parent distribution of wind speed. You don't need distributions of extremes, but you do need the parent distribution for wind speed and direction. So obviously one of the basic assumptions is that the general population of wind speeds generates the extreme wind events. which may not necessarily be the case. Certainly not the case if you've got a mixed distribution, as I showed in one of the earlier slides before. So in fact, not only that, I haven't shown you the complete development there, but there's many assumptions to get that formula. There are two different versions of it, one from Davenport and another one from LePage-Irwin 1985. In fact, the one I've shown there is from LePage-Irwin. And in that method, you need to calculate on the bottom line there, that's U dot amplitude average. So it's the average of the modulus of the rate of change of wind speed. Bit of a mouthful, but something needs to be calculated. Now they have come up with a kind of a general formula that supposedly applies to the whole world, but you find that it does vary from place to place, and it's quite difficult to calculate it. So it's got some problems and it's got some advantages. Well, when I was looking for a set of wind tunnel data to compare the two methods, the multi-sector and the outcrossing methods, I thought of a good example would be this international high-frequency benchmark building, or one of the two buildings. And if anyone was in Korea in 2012 at the AWAS ASAM conference, you might have heard me talking about that benchmark project. This was a set of data that was, two particular buildings that were used as benchmarks by 7 wind tunnel groups, and all the data was compared, and generally the agreement was pretty good for the base moments, X and Y moments at the base. So these are pretty well established set of data. So rather than just using one particular group, I averaged the wind tunnel data for the peak moments from the 7 groups for every 10 degrees, and developed those two equations there, the relationship between peak moment and wind speed. Now what we want is the inverse of that, actually, the UR as a function of a fixed value of wind speed. That actually defines a response boundary that I showed earlier in the outcrossing method. So the rest of the presentation I'll be comparing results from that building set in a particular location, assumed to, it's not a real building, but it's assumed to be located in a particular location for which we had pretty good wind tunnel, wind climate data, extreme wind climate and direction data. So we took the 180 meter tall benchmark building and assumed it was located near Melbourne Airport in Australia, for which we've got a lot of good climate data. Now I think about it, it's probably not a good idea to put a 180 meter building right next to an airport, but still, this is fictitious. So we assumed the building could have up to 8 different orientations with respect to the wind climate, with respect to north, as you can see there, and looked at every one of those cases and compared the multi-sector and the outcrossing methods of predicting the two base moments, mx and my. Now, in view of the limited time available for this presentation, I'm only going to show results from 2 of those 8 directions that I showed on the previous slide. There's a paper just been published earlier this year that will give you the full set of results, so we can follow that up. The reference will be at the back of the presentation. So what we're showing here is the predictions of the base moments, mx, the maximum mx moment and the minimum my moment, for the building orientated 0 degrees. So the y-axis pointing towards the north with respect to the Melbourne Airport wind climate. Now the multi-sector predictions are shown as a red line. The outcrossing method, the LePage-Irwin version of it, the results are shown as pale blue dots. And we have another set of symbols there which I've called direct calculation. So those have been obtained by not any kind of fitting, but making direct calculations of the peak moment for every year of data that was available, and just plotting those. So that's probably the benchmark that we try to compare our other two methods with against. So you see for both of those cases there, the maximum MX and the minimum MY, that both the multi-sector and the outcrossing give reasonably good predictions. Possibly the multi-sector is a bit predicts a little bit at the low end for the low values of average recurrence interval. So now we've turned the building through 90 degrees. So the y-axis is now facing east. And we've made the same predictions using both the multi-sector and outcrossing and the direct calculation approach, and plotted the predictions as before. Now in the case of the MX, both the multi-sector and the outcrossing do pretty well. They match the direct calculations quite well. But for the MY predictions on the bottom, the outcrossing doesn't do too well. It severely underpredicts the peak MY moments by about 20 to 25%. Now this, I didn't have time to show all the other 6 orientations of the building that we studied, but roughly for half of those orientations, for at least one of the MX and MY, the outcrossing does underpredict the correct values. So it does seem to have a bit of a problem. But on the other hand, the multi-sector method does quite well in every case. So now we come to the summary and conclusions. And I've listed those on the slide here. And since I'm running out of time, I'll leave you to read those. Now following this slide, there are 3 slides of references that myself and my co-author Chi Sang have found useful on some of these topics that we've covered. And right at the end I've left my email address, so feel free to email me with questions. So we come to the end of the presentation. Thank you for paying attention and listening for the last 45 minutes.